Welcome to our talk featuring the tool dtControl, which helps you represent controllers concisely using decision trees. What can you make out of this? It's not an abstract painting. Let's maybe zoom in a bit. Okay. It actually looks like there could be some text in there. Let's zoom in a bit more. All right. Now there might be enough information to make an educated guess. What I showed you right now actually is a controller produced through automatic synthesis by the tool Scots. In each line, you can see the state index followed by the set of actions that are allowed for this state. Automatic formal synthesis produces controllers which are correct for a given specification, but they are often large, obscure, and contain redundant parts, so they are unnecessarily over-consuming resources. Wouldn't it be great if we were able to get controllers which are not only correct by construction, but also small, explainable, and trim? In this video, we show you how our tool often achieves that, relying on two ideas. Firstly, we provide a better representation, namely decision trees. And secondly, we allow small changes to the controller that do not compromise safety. Before we dive into details, let's try to understand these advantages of decision trees on some examples. Consider the following automatic heating system that has 2 heaters and it has to keep 10 rooms all in a certain temperature interval. This is a standard example of the tool Scots. A correct controller for this, as synthesized by Scots, is a lookup table that has 26,244 entries. It is not only large and obscure, but as we'll see, also quite inefficient. The standard solution to the size issue is to construct a binary decision diagram, a BDD. If you ask Scots to do so, on a normal machine you get a timeout. Using a server with more power or a different approach, you can get a BDD such as this one. This is still large and even more obscure because now every variable is bit blasted. In contrast, if we construct a decision tree for the controller, we can get this picture. This is a tree with 7 nodes and only 3 decisions. Basically it says, if room 2 is cold and room 5 is cold, then we turn on both heaters. If on the other hand room 2 is warm and room 5 is warm, then we don't turn on any of the heaters. If only one of the rooms is warm and the other is cold, then we turn on the heater in the respective cold room. And this is a safe controller for this system. It can be that simple. We were not able to see this in either of the 2 previous formats, but this decision tree is now so small and the structure of the tree so clear that we can actually explain what happens. From this, we get 2 additional positive effects. Firstly, since it is so small, the controller actually only needs to transfer 2 bits over the wire. Without this controller, there were many more available actions, since heaters could be turned on to certain degrees, yielding a combinatorial explosion. But here, these 4 possible actions can be encoded with 2 bits. Secondly, we see that to stay safe, we actually only need to measure the temperature in room 2 and 5. So we can save 8 of the temperature sensors. This automatically trims the controller, reducing both its complexity and the deployment cost. Let us consider one more example to highlight yet another advantage of decision trees. On the tree we had so far, the decisions were really simple, but this need not be the case. Consider this adaptive cruise control with 2 cars, ego and front. We want to control the acceleration of ego such that it never comes too close to front. The lookup table and BDD for this controller again are incomprehensibly large, even larger than in the previous example. In contrast, a decision tree for this problem can look like this. Again, you can see that it is small, but right now we have these huge predicates here and here, which look pretty scary. However, using the domain knowledge, namely kinematic equations, they turn out to mean worst case distance if we accelerate for one time step, and worst case distance if we stay neutral. If this distance is less than our safety margin, we can only decelerate. Consequently, again, this tree is a lot more explainable than a BDD or a lookup table. In fact, coming up with these predicates made us identify a bug in the model that prevented us from decelerating if the car in front was far away. To summarize, we have seen that these trees can be small, explainable, and highly beneficial in several respects, such as for optimizing memory, bandwidth, cost, or for validation. But how do we actually come up with them? As already mentioned at the beginning, the two key elements are the decision tree representation and distilling the essential part of the controller. Concerning the first one, why should a controller be concisely representable in the first place? The reason is that the state space is typically structured, given by many variables. In such a case, we might be able to group together states performing the same action. So let's take a closer look. We have a lookup table here, which assigns a control input to each state based on the values of the two variables x1 and x2. Observing the values of x1 and u, we immediately realize that in this controller, if x1 is greater than or equal to 6, the action 1 may be used. On the right, we draw a decision tree which encodes this information in the true branch from the root. Since we have taken care of the first row, it remains to encode the remaining 3 lines of the controller. Observe that when x2 is less than or equal to 2, the controller allows the non-deterministic choice between 0 and 1. As before, we indicate this in our decision tree. Finally, the action 0 is allowed in all the remaining states, so we finish off the decision tree by adding a node which recommends using the action 0. What we have just seen can be automatically achieved through decision tree learning. Given a controller in the form of a lookup table, we can interpret it as a machine learning problem of assigning labels, which are the control inputs or actions, to items, which are the states. This classification problem is then solved using decision tree learning. We can force the learning procedure to exactly represent the controller, which means without loss of any information. Note that, to this end, overfitting is actually very desirable in our setting in contrast to standard machine learning. Now, what if we are ready to sacrifice a bit of permissiveness to obtain a controller that is still safe but even smaller than this one? Observe that we can resolve our non-deterministic control input to either 0 or 1. If we resolve it to 0, then we can group its node together with its sibling and obtain this very small tree. In our tool, we offer many determinization techniques, such as the standard selecting inputs with the minimum norm, or resolving the non-determinism randomly. Alternatively, you can use our own dedicated and extremely performant determinization technique MaxFrec, the details of which are available in the paper. Besides, in the case of probabilistic systems, we can also sacrifice a bit of precision and further dramatically decrease the size of the controller, as shown in previous work. While a minute ago we constructed a tree by hand from the lookup table, you might wonder how to do it algorithmically in a satisfactory way. This boils down to asking, where do the predicates in the nodes come from? And this question in turn has two parts. Firstly, what is the domain of the predicates we consider? And secondly, how do you choose from the domain? For the first part, dtControl offers the standard axis parallel splits, as well as the more complicated oblique ones. These allow linear combinations of several variables. Once the domain is set, dtControl offers various heuristics, so-called impurity measures, to assess the quality of the predicates. This includes the standard impurity measures from machine learning, information gain and Gini index, but also some newly developed specialized heuristics. We summarize the working of dtControl in this diagram. The core modules include the determinizer, which allows one to preserve or reduce permissiveness of the input controller. The predicate generator sets the domain from which predicates are generated, and the predicate selector evaluates the impurity measure of each predicate at each node. The three modules are orchestrated by the decision tree learner. dtControl can take inputs from various formal synthesis tools such as Scott's, UPAL or Prism, and it also makes it easy for you to build a pipeline from your favorite tool. As output, we can produce the graphical output you saw throughout the presentation, or we can produce equivalent C code, which is nothing but an if-else statement for each node of the decision tree. How well does our approach perform in practice? To find out, we tested it on 6 permissive and 2 deterministic controllers. Here, we give their sizes as lookup table. As a competitor to our approach, we constructed BDDs. We differentiate between BDDs keeping all the information of the controller and BDDs for a smaller determinized version of the controller. We invested a lot of resources to come up with a very good BDD. To that end, we tried many initial variable orderings and then called reordering heuristics until convergence. In each cell, we report the best number. Similarly, for decision trees, we report our best number when keeping all the information and when using our new on-the-fly determinization. For the permissive controllers, we see that decision trees and BDDs roughly match in size, so both are efficient representations of controllers. However, when using our new determinization, the decision trees become so small that in several cases you can just draw them on a piece of paper and understand them just by looking at them. To summarize, decision trees provide a compact representation of automatically synthesized controllers immediately competitive to BDDs, but they also allow for further reductions with significant effect, such as through determinization. Another key effect is the explainability of the controller and the high degree of structure, which we can utilize in different contexts, as seen in the previous examples. Our tool is open source, and we're happy to help hooking it to your synthesizers, as well as receive your wishes for further functionalities. Thanks for listening, and goodbye.